What I'd like to talk about today is a brief introduction to regression analysis, and what I'm going to be doing is first talking a little bit into the camera, but then what I'm going to do is move the camera over just to show what I'll be writing on a piece of paper, and I'll talk over that. I think it's easier if you see it. It's pretty low tech to be using a camera like this, and I hope you'll bear with me, but I think the concepts and ideas are pretty straightforward. You should be reading or have read or printed out that regression one-page handout that's on the Angel website, and you are very much encouraged to read the short article by Sykes, also on Angel, that explains regression analysis, going through it step by step. It's a very good introduction, and I think it'll be very useful for you to read it, watch this video, read it again, watch this video again. By doing that, I think you'll have a really good understanding at the end of what regression analysis is. The purpose in this class is not to know everything about regression analysis, especially the statistics underlying it, but rather to have a good intuition about what it's doing, and then know how to interpret the coefficients in a regression, and how to do some minimal intuitive evaluation about whether a regression that you'd be looking at in an academic paper is justifiable or not. So that's basically what we're going to do. In regression analysis, we typically start with data, and we'll organize this data as observations, and we might think of graphing the data that we have. If we have data that consists of two things that we measure for each observation, one thing that we measure we'll call X, and another thing that we measure we'll call Y, and we can think of plotting the observations of X and Y on a graph, where each point is a combination of X and Y that pertains to an observation. So the observation might be the household. So each point here would represent combinations for different households. The X might be the gender of the household head, male or female. In this case, though, it would be a continuous variable, so it might be the age of the household head, going from 20 to 70, and the Y might be how many children are in the household. And so we would expect, as we see here, that the older the household head, the more children the household has. So those are pairs of observations of variables for each unit of observation, for each household. The observations might be on countries. The X variable might be, in a graph like this, might be how mountainous the country is. That is, what fraction of the country is mountains. The Y might be how many ski lifts there are in the country. And so again, countries that were more mountainous, where X was a larger number, would be associated with higher Ys, more ski lifts in those countries. So data like this we can look at when we plot it visually when we have a pair. When we have more than a pair, it gets more difficult to plot that data. So part of what regression analysis is about doing what we do in terms of organizing the data for two observations, doing that to data sets where we have more than two variables for each unit of observation, where it's more difficult to graph the data, but we still want to summarize it in some meaningful way. So we're going to use the example of the 2 by 2 data, but we will, with X and Y data, to motivate and explain the regression, but you'll recall and always keep in mind that the major use of regression is when we have more than two variables. If we just have two variables, we can always just plot the graph of the two variables and sort of see with our own eyes what the relationship looks like. It's when we have more than two variables that we really need regression analysis. these two variables, or generally the variables that we're being interested in, have names, and we call them a lot of different things. The y variable, in a usual analysis, will focus on one y variable. We'll call it the endogenous variable, or the dependent variable, or the outcome variable. And that's the one that we're interested in explaining. The x variable, or typically multiple x variables, we'll call the exogenous variables, or the independent variables, or the explanatory variables, or the covariates in a regression analysis. So here we again just graphed one x and one y. Typically we'd have multiple x's and a single outcome. Sometimes, though, we'll have multiple outcomes that we'll be interested in explaining. We'll have to use techniques that we won't get into in this class when we have multiple outcomes and multiple explanatory variables. For most of this class, we'll keep it simple. We'll have one outcome that we're interested in and a bunch of explanatory variables, or exogenous variables, independent variables. So what we're going to want to do typically is look at the data that we have, and when you look at it visually, of course, you notice that there's an association between the x and the y. It's pretty obvious from visual inspection that there's a correlation between the x and the y. And we typically would be interested in understanding, well, what's the magnitude and statistical significance of that correlation? And how can we calculate that? Well, for just two variables, we can calculate the correlation coefficient, but when we have more than two variables explaining an outcome variable, we'll need to use regression analysis. So what regression analysis, the simplest way to think about it, is fitting a line to the data that we have. And we'll call the slope of that line the coefficient. That is, it represents how much a change in the x variable is associated with a change in the y variable. And we'll try and fit a line that does a good job of capturing the pattern in the data. So if we didn't have any mathematical technique and this was the data that we were looking at, we could just say, this data certainly looks like a line that goes like that, fits the data pretty well. The slope of this line, the rise, change in x, change in y over, or change in x, the rise over the run, it's the slope of the line, describes how much a change in x is associated with an increase in y. So pretty simple. We usually won't care very much about the intercept down here, about where our line intercepts the y-axis. That usually has no economic significance. We'll usually only be interested in the slope of this line. And we'll usually call this slope beta or b. Sometimes to say that it's an estimated slope, we'll put a hat over it, beta hat or b hat, to indicate that that's our estimate of the slope. And our estimate right here is our eyeball estimate. But we want a more systematic way of estimating this slope. If the data weren't so obviously upward sloping, we might have a much harder time figuring out what the right slope is. So let's think about a system, an algorithm by which we could calculate what the slope is of a line according to some fitting criteria that we might have. So here are two lines with some data in the middle, and we might ask ourselves, what is it about these lines A and B that our intuition tells us they don't fit the data? Right? They're far away from the data in some sense. We wouldn't say that, yeah, A is an accurate representation of the data here, or B is an accurate representation of the data. They plainly are not things that we would say. And so we ask ourselves, well, they're not good representations because they're far away from the data. And other lines that we might think of having are even farther away. So our criteria for asking whether a line fits the data is some kind of distance criteria. How far is the line that we fit to the data, how far is it from that data? Well, there's lots of different ways we could measure that distance. We could measure it in the sense of taking these points and going perpendicular to the line that we're proposing and adding up maybe all of those distances. That would be one method that we could use. Another method we could use would be to go horizontal and take each point and measure the horizontal distance to a line. And finally, we could measure the vertical distance to the line moving along the y-axis. So there's three different possibilities that we could have for measuring distance, and obviously there's an infinite number of distance measures we could think of. Instead of taking straight lines, we could say hemicircles. What's the distance of every hemicircle to the line that we are interested in? That criteria may have no intuitive sense, and we reject that kind of a criteria. It turns out, for our purposes, that the vertical distance is the distance that we'll most focus on. And I'm going to draw you another graph to show you what that vertical distance looks like. So here's the data that we have. Sorry for the bounciness of the picture. And we draw a line through it. And now we can think of measuring all the vertical distances, both on top and on bottom of the line. And we'll often call these vertical distances the error, and represented by an E. And thinking that we have different x values, and our line tells us what the predicted y value would be for that x value. So if this is our x value, x1, we go up to the line and we read off what the predicted y value would be for that y1. But this point was an actual observation of x1 and a y over here. This was the actual, this was the predicted. So the difference between the actual and the predicted we'll think of as an error in our line. Our line didn't do a good job of fitting this observation. So all these distances here are the errors associated with choosing this particular line. If we'd chosen a different line, we'd have a different set of errors. So we could add up all these errors and say that that's some measure of our distance. Turns out, for various reasons, that that's not a very good way to add them all up. So instead we'll square them. Notice if we add them all up, some are positive, some are negative, they'll just cancel each other out. So what we'll do instead is we'll take the square of each error. So we have an error here, we'll take the square of that. The square just means you multiply this number by the same number. And we'll say that the line that minimizes the sum of the squared errors is the best fitting line. So the beta hat that we want, our estimate of the slope, is the one that minimizes the sum of squared errors. And that's why you'll often hear a regression being referred to as a least squares regression. It has the least sum of squared errors. So in our usual case, we're not going to be interested in estimating the slope of a single line relating one variable x to one variable y. If we were to write this as an equation, we would write y equals alpha plus beta x. Remember, that's the equation of a line. Alpha is the intercept, and beta is the slope of the line. And my son is in 10th grade, and so I know that they're learning this. He's 10 years old in 5th grade, and they're starting to learn this stuff, so I know that you know it too. And if you've forgotten it, what the equation of a line is and how to graph a line, go back and look at your middle school and high school geometry class. It's very straightforward. Remember, as long as we're at it, we'll just do a little bit of a math review. We can think, suppose we had values for the intercept and the slope. Suppose we said that the intercept was equal to 2, and the intercept were 2 and the slope were 5. Our equation would look like y equals 2 plus 5x. So we could then go, if x equals 1, then y equals 7. If x equals 2, then y equals 12. If x equals 0, y equals 2. If x equals minus 1, y equals minus 3. And we could graph that line when x is equal to 0, y is equal to 2. So that point is this point here, point 0, 2. If x is equal to 1, y is equal to 7. So this is 1, 7. And we only need 2 points to draw a straight line. So our equation looks like this. The line of that equation looks like that. That's what we'd be estimating if we just had 2 variables. If we had more than 2 variables, we'd have something like y equals alpha plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, where each one of these x's is a different variable, and we're estimating beta 1 hat, beta 2 hat, beta 3 hat, each one of these coefficients.